As I explained when we were talking about Chapter 15 and Chapter 16 are very related. If we know that two variables are correlated, then if we have information about one of those variables, we should be able to make predictions about what's going to happen to the other variable. And it's that principle that underlies Chapter 16. Chapter 16 has an unfortunate title. It's called Introduction to Regression. Right away, regression seems to mean, oh, we're going backwards. Well, no, we're actually going forwards. So when you see the word regression, in your mind, just substitute the word prediction. Because that's what we're trying to do when we know there is a correlation between two variables. We're trying to predict. So we'll substitute prediction for regression. In the last chapter, we learned that we're studying the Pearson correlation, which is the correlation that we use when we think that two variables have a linear relationship, or when we think the best model or the best way to describe the relationship between two variables is linear. When we think that, we use the Pearson correlation. There are other correlations for nonlinear relationships. We're only studying linear relationships. Regression then, and we're going to use the word prediction instead of regression. Prediction is a statistical procedure that helps us determine the equation of a straight line so we can use it to make predictions. Think back to when you were taking geometry in high school. We learned that various geometric figures have equations associated with them. We have parabolas, we have equations for all sorts of different types of geometric figures. Well, we also have an equation for a straight line. And the equation for the straight line was, if you want to predict a y variable, find the slope of the line, multiply it times the x variable, and add where that line crosses the y-axis, which is a. So any straight line then, a straight line that looks like this, a straight line that looks like this, a straight line that goes this way, can be represented by that equation. Y equals bx. B is the slope of the line. A is where it crosses the y-axis. So this line that I'm drawing now, this circle right here is A. It's where it's crossing the y-axis. And the slope of that line is b, or beta. B is the slope. You can have different kinds of slopes. We can have a slope of a line that's at a 45-degree angle. That represents a very high correlation. As you go out 1 point on one variable, you go up 1 point in another. We could have a slope of the line that looks like that. In this case, you'd be going out several points on x for maybe a smaller increase in y. The correlation isn't as high. We can have a slope of a line that looks like that. The equation for those lines, which allows us to predict the y variable from knowing the x variable, is beta. And where that line is going to cross the y-axis, we have to know that to know exactly how to draw that line. That's called the y-intercept, which is indicated by A. And what this chapter is explaining is how you compute B and how you compute A from the data that we derived from when we were computing a correlation. So the figures that you computed to get a correlation coefficient, the sums of the products, the sums of squares, they'll be used for when we're computing the B constant and the A constant. This would be an example of what a regression graph looks like, or a prediction graph. Remember from last chapter, each of these points represent a person's score or an individual score or whatever we are studying in our research. It could be a building, it could be a country, it could be a school, it could be a person. But each point represents the score, and let's say we're dealing with a person here because we're dealing with SAT scores and grade point average, which is what is listed on your y-axis. Each of these points represents a score for SAT for that person and the person's grade point average. So this individual right here scored 420 on the SAT and got a grade point average of 2.0. This person here scored about a 620 on the SAT and got a grade point average of around 3.6. So we have each one of these points then represents a person's pair of scores. They don't form a perfect straight line, but when we draw the boundaries of the scatter plots of the points, it seems to resemble pretty closely a straight line. A straight line seems to be the best fit for all those points. So we're calling this regression line, this line right here, the line of best fit. The SAT scores are our x variables. When we're doing prediction, the x-axis is what we're trying to predict from, and the y-axis are what we're trying to predict. So we're trying to predict what your grade point average would be if we know your SAT scores. And it looks like there's pretty good prediction. If we know, for example, that someone has an SAT score of 580, then if we go up to the regression line and go directly over to the y-axis, we're predicting that this person will get a grade point average of about 2.75. There'll be errors in prediction. For example, this person scored 580 but got a grade point average of 2.2. This person scored about 580 and got a grade point average over 3. So we're not always going to be perfectly accurate when we predict a grade point average of 2.7 from someone who got a SAT score of 580. But we'll be better making that prediction than if we had no information at all. And the value of your model, you're modeling these data points with a straight line. We'll talk about how you know whether that model has any good prediction or whether the prediction is good or whether the prediction is poor. These are 3 points that I'll be demonstrating on the next slide. But if you think of points being scattered, these represent people, 2 scores. And I want to build a model to make predictions, and I'm going to use a straight line. How well this model predicts can be measured by calculating the distance of each point from the straight line. The greater this distance from a point to the line, the more error there is. Because for this x value here, I'm predicting this y-score. Well, all of these are potential y-scores. And the farther the actual y-score is from the line would be the error that it's involved in prediction. And the greater the distance between each point and the line, the more error I have in my model. It would be nice if all my points were right on a straight line. Then when I modeled it, I would model it with a straight line, and I have very, very little errors in prediction. But when my scatter points are spread out, which is always the case, we don't have perfect linear relationships, then we're always going to have some error involved in prediction. And the total amount of error you get by measuring the distance between each point and the line and squaring that distance, and then adding up all those squares, kind of like a sums of squares. And the regression equation that you develop is meant to make the distances between any point and the prediction line as small as possible, and that's called the least squares method. If you look at these two examples, we have our x variable. Another name for the x variable is the independent variable, and another term for the y variable equals the dependent variable. We're saying that y scores are dependent on x. That's why y gets the dependent variable. X is always your independent variable. In this case, before we drew the line, we had these points that were lined up perfectly straight with one another. And so we solved the equation for that line and drew the line, and the line goes right through all the points. There's hardly any errors in prediction. You'll get excellent prediction. If you know what someone's x score is, you'll predict very accurately their y score. On the other hand, if we look at the model on the right, we have our x independent variable and our y dependent variable. This represents someone who scored 2 and 3. Well, and this represents someone who scored about a 2.3 and a 9. We don't have the points nicely lined up in a straight line. So when we draw our line of best fit through the middle of the points, we're going to have some error. And as you can see, the actual score that the person got on the y variable is pretty far from the point on the line that we would predict. This person who got 2 actually scored 3 when we would predict that person to score a 6. So we have errors in prediction, and the farther the points are from the line, the more errors in prediction we have. The higher the correlation between x and y, the closer these points would be to our line. In order to solve the regression equation, we have to, which is to predict y, which is why you have y hat, we have to know the slope of the line, which is b. We multiply that times the x variable, and then we add to that the y-intercept. To get b, we have to divide the sums of the products, which you learned about between x and y, which you learned about in the previous chapter, by the sums of squares for x. So on the way to computing the correlation, you already calculated the numerator and the denominator. And if you divide the sums of squares for x, for the x variable, into the sums of the products, you'll get the slope of the line. And if the correlation is negative, the slope of the line will be negative. If the correlation is positive, b will be positive. The correlation coefficient and b are closely related. So we know the slope of the line from b, but then in order to determine exactly where that line is, how to draw that line, we have to know a, which is where it crosses the y-axis. So let's say that this is a slope, and this is a, the exact point where it crosses the y-axis. To determine a, we take the mean of y, which you computed when you were doing the correlation, and we subtract from it b, which you did here, which you computed there, times the mean of x. Multiply beta times the mean of x, subtract that value from the mean of y, and you will get the y-intercept. And now, when you determined a and you determined b, you now have the constant for the equation. So if someone says the person's SAT score is 400, what would you predict this person's grade point average to be? Multiply 400 times b, add the y-intercept, and you will get their predicted grade point average. Your book gives you a number of examples of how to compute b and a. Make sure you understand them. The question, though, is how important is the correlation coefficient? How well does it predict? the correlation coefficient, the relationship between the x and the y variable, the model that we develop. Some models are good and some models are bad. Some models predict well and some models don't predict so well. So let's say the correlation is 0.6. How good is 0.6? We could have a correlation between an x and a y variable of 0.2, and we develop a model from 0.2. How good is that? Well, let's try and understand it this way. This circle is going to represent the grades in our class. And the circle represents 100% of what determines the grades that you're all getting in this class. We get different grades, we get different numbers correct on the tests. Why? Why do we have differences? Why isn't everybody scoring the same? Well, everybody's not scoring the same because people are different. Some people study harder than others. Some people have better math backgrounds. Some people have more time to work. Well, there are a variety of reasons why the grades differ. So the question then we're asking is why? Why do grades differ? What determines why grades vary? Well, let's think of the various reasons. One reason's grade vary is because some of you have stronger math backgrounds. You've had more math courses. Another reason why grades vary is some of you simply have more time to study. Another reason why grades vary is because some of you have higher aptitude than others, your SAT scores. Another reason why grades vary is some of you are motivated more than others. And we could go on and on and on. Some of you are healthier. Your health in some way will determine how hard you can work. So we have a variety of reasons. And the question that we ask is, well, if we wanted to know what percentage of the grades, what percentage of why people vary is determined by aptitude alone, or what percentage is determined by the amount of time that you spend, what would you imagine it to be? So you say, well, I think that the percentage of the grade that's determined by how much time we put into it, how much effort, how much time we're spending reading the lessons and so on, is 25%. Or someone else might say, no, I think it's only 10%. The other 90% is accounted for by other sorts of things. How do we do this scientifically? Well, if you correlated the amount of time that people put into the class with their grade, x equals the amount of time, and y equals the grade that you got. I've done this in the past. The correlation is about 0.6. The correlation between the amount of time and your grades, and here are the points, and I could draw a line through it, is about 0.6. Well, how important is that? If you square it, 0.6 times 0.6 equals 36%. What that is saying is that 36% of why people get different grades is explained by the amount of time that they're putting into the class. That's pretty substantial. Now, the total is 100%, so 64% is not explained. Well, if 64% is not explained by how much time, what goes into that 64%? Math aptitude goes into that 64%. Health goes into that 64%. cognitive ability goes into that 64%, but 36% is explained just by the amount of time that you put into the class. It's not a perfect correlation. There are many of you in this class who are putting hours and hours and hours, and your grades aren't that high. Some of you are putting in hardly any time and getting very high grades. But for the most part, the more time you put in, the higher your grades. The less time you put in, the lower your grades. R squared, and this is explained, I think, on page 524 in your book. R squared is called the coefficient of determination. How much of your grade point average is determined by your grades? Now, a dependent variable, our y variable, are your grades. Our x variable, or your independent variable, is the time you spent working on the course. And how much of your grades is explained by the amount of time. So one of the ways that question is asked is, what percentage of grades is determined by time? Your book phrases that slightly differently, and it says, how much variance in both of these, this expression here and the expression that I'm writing now, are saying exactly the same thing. How much variance in y is explained, E-X-P-L-I-N-E-D, is explained by x. How much variance, how much of the reason why people vary in the y scores, in the dependent scores, in this case in grades, is explained by the amount of time that they put into the class. How much variance in your grade point average here at the University of Texas is explained by the SAT scores that you came in with. How much variance in your grade point average at the University of Texas is explained by your health. How much variance in your grade point average is explained by the quality of your high school or the quality of your teaching. We would have to correlate X and Y. We would have to correlate grades and time spent studying. We would have to correlate grades and a rating of the quality of your high school. We would have to correlate grades and the amount of income in your family, and then use one to predict the other.